In this section, we are going to talk about closures and iterators. These two are often found inside of functional programming languages. Closures are a function-like construct that you can store in a variable, and iterators are a way of processing a series of elements, which is something we have seen and done before in this course. So let's dive right into what closures and iterators are. Closures are anonymous functions, which are functions without names, that we can save inside a variable or pass as an argument to other functions. The best way to learn this is by doing it, so let's get some code going, because I believe the best way to learn closures is to see how they are useful. So let's create a sample program and then refactor in closures. So the first thing I want to do is create a new struct called city. And then here we're going to have the city name, which is a string, and then the population, which is going to be an unsigned 64. And then we're going to create a function called sortPop for sort population. And then in here we are going to take in a vector of type city, and then we'll just call city.sort. And we see that we're already getting the red squiggly line error, and if we hover over it and scroll down to the bottom, it says standard CMP for compare ORD is not satisfied. So for us to be able to do this sorting, we need to create a helper function. So I'll call it pop helper for population helper, and then in here we'll take our population and it will be a reference to a city, and then it's going to return our unsigned 64. And then in here we'll just take our pop.population. So now we can come back up here, and instead of saying sort, we'll say sort by key, and then we'll call our pop helper function. So now if we come down here, let's get some sample data going. We'll say, and we'll just keep our cities very bland and not fun at all. We'll create a new city, call it city, and our string and our city name is going to be A. Very creative, I know. And then our population, we'll give it 100. It's a very small city. So now we'll do this, and we'll just create a few of them. And we'll go to, and then we'll be B, C, D, and E, and then we'll just fill in here as well. C, D, and E, and let's change up our population some. We'll go 57, we'll go 140, have a population of 5, and then our last city will have a population of 70, and then we'll create a new mutable vector of type city, and we will initialize it, and now we'll just push in all of our cities that we created. And we have B, C, D, and E. So now let's call our sort population method, and we'll pass in our vector. And then we want to be able to print out our vector sorted, which we can do as such. And it looks like we have a little error. Oh, derive debug. So we will add that in. and now our error is gone. Okay, awesome. So now if we run this, we expect our vector to be sorted from least population to greatest, which we can see population 15, 57, 70, 100, and 140. So we see that it is sorted in ascending order, which is what we wanted. But now let's see how we could have done this using a closure. So what we can do is come here and we'll just go ahead and just comment those two out. And now we'll create a new function called sort pop, and then we'll just put closure in here. That way we can differentiate our functions, and we'll have a reference to a mutable vector again of type city. And then in here we will say pop sort by key, so the same function, and now we will create our closure. So we'll have the two vertical lines, and then inside we'll have P. And in this case, P is going to be our argument into the closure. And then we'll do P dot population. So we're passing in our P parameter, and now we have access to the population, which is obviously inside of our city struct. And now if we run it again, sort closure, there we go. And now if we run it, we see that we get the same exact output with the order being in ascending order. So this is just was a super simple way of showing where closures can help us out. We were able to go from, and this was a simple example, but from 2 functions down to 1, and we were able to contain all of our logic inside of 1 line. Obviously, closures can do much more, so let's look at how we can further use closures and a little bit more of the details into how closures work. As you might have noticed, closures do not require us to annotate the types being used. Because closures are typically short and have a narrow context, the compiler is able to reliably infer the types of parameters being used as well as the return type. But we can still annotate the types if we wanted to. So to see an example of this, we'll create an add closure, which is going to accept a parameter of type I32, and then it's going to return an I32, and then we're just going to have it add 1 to the value we get. But as we already saw, we also don't have to have annotations. So I'll create the same closure, and I'll just call it add v2 for version 2, and we'll accept in our x argument, and then we'll just add 1 to it. But as you can see, this x is underlined, and it says a type annotation is needed. Well, in order for the compiler to infer what type it will require, we actually have to use it. So in this case, as soon as we call it and then pass in a 1, it's able to infer, hey, we are using type I32. But once we let the compiler infer the type, then that is the type that must continue to be used. Otherwise, it will create an error. And we can very easily see an example of this, and we'll create a closure that accepts 1 argument, and then it's just going to immediately return it. So we'll say let string equals example, so we're calling our closure, and then we're going to pass in a string called string. And the closure, as you can see, is completely happy with that. But what if we try to pass in a number now to example? Well, we see the 2 is underlined in red because it is expecting a string, which was the first type that was inferred. So we can see that by hovering over it, and it says expected string found an integer. And that's really all there is to it for closure type annotations. So now I want to take a quick minute to discuss closures performance. Rust's closures are designed to be fast. Closures are not allocated on the heap unless you put them in some kind of a container, such as a vector. And since each closure has a known type, whenever Rust compiles the code, it can inline that code for that particular closure. Inlining is a technique where the compiler will add the closure inside the calling function's block. And this prevents another separate function call from happening, which is going to give us a performance optimization. So if you are creating a program that is extremely performance dependent, closures are still very acceptable to use in the right situation. This lecture is going to be a bit more of just talking and not much coding, as these are important concepts to understand. With that, there are 3 traits that we need to cover. We have fn, fn mute, and fn once. Fn is the family of closures and functions that you can call multiple times without restrictions, and it borrows values from the environment immutably, and this is the highest category, and it includes all little f, includes all fn functions. Fn mute is the family of closures that can be called multiple times if the closure itself is declared mute and mutably borrows values. Fn once is the family of closures that can be called once if the caller owns the closure, and then the once part of the name is because the closure cannot take ownership of the same variables more than once. So every big F, fn, meets the requirements for fn mute, and every fn mute meets the requirements for fn once. And this means that fn is a subtrait of fn mute, and fn mute is a subtrait of fn once. Therefore, we can conclude that fn is the most exclusive and most powerful trait of the 3. So let's take a look at 3 separate closures and try to establish which trait each example falls under. So the first example is going to be a closure that takes no parameters and then drops a value. The second one is going to take an argument and then check to see if a vector contains the argument. And the last one is going to also take an arg, and then it's going to push into the vector that arg. So take a second and try to establish which trait goes with which example. Alright, so the first example is going to be fn once, because we can only drop the value once. The second example is going to implement fn, because all we're doing is checking to see if the vector contains the parameter that was passed in. There is nothing required in this that needs to be mutable. And then lastly, this is fn mute, because the vector would need to be mutable in order for us to push the argument into the vector. And that's really all there is to it for the fn traits. So now let's talk about copy and clone with closures. The rules for copying and cloning work like the regular copy and clone, and Rust will automatically figure out which closures can implement copy and clone and which closures cannot. So let's take a look at 2 simple examples. So for this one, we're going to create a value y, assign it 5, and then we're going to create a closure here that's going to take an argument and then add it to our y value. And now we're going to take a copy of the add y closure we created. So this is closure being copied. And now we can check to make sure that our copy actually worked correctly. So we can say add y, and then in here we can also call copy, and we'll give it the value 10. So if this copy works correctly, we would expect 20 to be printed out, because here where we designated that the closure is being copied, we are going to add 5 to 10, and then on the outer call we're going to add 5 to the now value being passed in of 15. So if we run this, we got the expected output there of 20. So now let's create an example where neither copy nor clone works. So we'll actually take this and we'll modify it a bit just to keep our example very similar, and we'll put mute y, and then we'll do a mutable add y, and then we'll also even make copy mutable, and then in here we are going to modify the logic being done. So we're going to say y is going to plus equal x, and then we want to return y. And we see that this is already not going to work, but if we run it anyway, we see that the value was borrowed here after a move. And remember that this does not work because mutable values do not implement copy or clone. So that is why this does not work, even though our changes were very minute. But all in all, closures are not overly complicated. And I know that the past few lectures were more theoretical than it was hands-on, but we will actually see where closures shine in the next topic of iterators. We have already used iterators some in previous lectures, but just to refresh, let's see one really quickly. So we'll create a vector, and we'll use the vect macro, and we'll just say 1, 2, and 3, and it helps if I use the correct brackets. And then we can say for val and vect.iter, print line, and then print the val that is in the iterator. So we'll say cargo run, and we see 1, 2, 3 being printed out. So all iterators are going to implement a trait named iterator, which is defined in the standard library. The trait looks like this. So we have trait iterator, and then we're going to have type item, and then we have fn next, which is going to be a reference to the mutable self, and it's going to return an option of self item. And then there's many default methods available to us once we implement next. So item is the type of value the iterator produces, and the next method either returns a sum with a value contained in it, or it's going to return none to indicate the end of the sequence. And then we also have the into iterator trait. And any type that implements into iterator is an iterator because it's something we can iterate over by calling the into iter method. So let's look at an example of this. And I'm just going to comment that out. And we'll comment this out as well. So we'll create another vec called vec2. And in here, we'll do the same thing, 1, 2, and 3. And then we'll say let mute iter equals a reference to our vec. And then we'll say into iter. And then while let sum v equal iter.next, which is the method given to us here because we created an iterator this way by calling the into iter method, we can now print out the values inside of sum v. And if we run this, we expect the same output of 1, 2, and 3. Great, which is exactly what we got. So, just to clarify, an iterator is any type that implements the iterator trait, and an iterable is any type that implements into iterator. Now remember, last lecture I said closure sign when using iterators. So let me expand on that. So we will comment all of this out. And up here, I'm also going to just go ahead and comment all of this out, as well as that, and as well as these. So I want to create a new struct called item. And in here, I want it to be a string that has a name, and we're also going to give us the derive debug trait here as well. So now we're going to create a function that's going to be called check inventory, and we're going to accept a vector of items, and then we want to check to see if a product exists by accepting in a string, and then we'll return back a vector of items. And then in here, we want it to be items.into iter, so create an iterator. And then we want to filter, so now we have another iterator. So as we see here, it creates an iterator for us. And this is where our closure is going to really help us. So we'll accept in a parameter, and then we want to check to make sure that name equals the product, and then to return it back to us in a vector, we want to collect on this. So in here, we'll create a vector of type vec_item, which is going to just be a new vector. And so now we'll push in some values. So we'll push in an item, and then in here our name is going to be a string from, and we'll have a coat in this case. So now let's push in a couple more additional items. We'll have and we'll add in our semicolons, and now we'll have a shirt. We'll have some shorts, and we'll have some shoes. So again, a very simple little example for us to kind of understand what's going on. So then we'll say let checked equals check inventory. We'll pass in our vec, and then we want to see if we have a string from shirt. So we want to see if we have a shirt in stock in our inventory. And then we will print out what is returned to us. So let's run this and just see what happens. So we see that we have an item with the name shirt returned to us. So let's go back up here and kind of look at what we did. So we use an into-iter to create an iterator that's going to take ownership of the vector, and then we call filter to adapt that iterator into a new iterator that only contains elements for which the closure returns true. The closure captures the product parameter from the environment, and it's going to compare the value with each item we created and only keeps the item we specified, which in this case was a shirt. So it's only going to keep the item that is a shirt. And then we call collect to gather the values returned by the adapted iterator into a vector that will be returned from the function. So we used a closure in this case to quickly evaluate logic without having to do a separate function call, which allows us to keep our code clear and concise. So that is one of the ways that a closure really shines when we use iterators. We're able to quickly and efficiently have short and concise logic in order to evaluate values coming into our closure. But now, what if we wanted to create our own closure? Our own iterator. So we'll create another struct, and we'll call this one a range, and we'll give it a start, and then it'll be unsigned 32, and then we'll give it an end of unsigned 32 as well. And now remember, we have to implement an iterator for range, and now we need to implement the trait. So we're going to have type item, and it's going to be unsigned 32, and now we need to implement next. So we'll have a mutable reference to self, and it's going to return an option of self item. Is that how it was? Yes, self item. And here we will say if self.start is greater than or equal to self.end, then we want to return none. Otherwise, let result equal sum self.start, and then self.start, increment it by 1, and then give us the result. So to check to make sure that this works for us, let's create a range, and we'll give it a 0 to start, and then we want our end value to be 10. And then we'll say for r in range, we want to print out the iterator, and we want this to be a little r. So now if we run this, and we now see 0, 1, 2, 3 all the way to 9, which is perfect. So now we know that our iterator is working for our range struct. So I also said that we should get some default traits, some default methods once we implement in the next function. So let's check to make sure that we did that, and then that would also prove that we got our implementation done correctly. So we're going to call range.filter, which is a function given to us if we implement next correctly. We're going to pass in a parameter, and we only want values where when that parameter modded by 2 equals 0. So that means when the values divided by 2, our remainder is 0. And then we want to collect, that way it is stored inside of our vector. And now if we print this vector out, we would expect all the values that when divided by 2 equals 0. And we see that we get 0, 2, 4, 6, 8, which is correct. So that's really all there is to it for iterators and closures. We see that we can use closures to allow us to easily perform logic on values inside an iterator. In the next section, let's continue on and start learning about smart pointers. I hope you enjoyed this section on iterators and closures. In this video, we are going to go over the solution to the assignment for this section. The assignment was to create a vector with the values 1, 3, 5, 7, and 9. Then use an iterator and a closure to multiply all of the values by 10 and store the result in another vector, and then print out the vector to confirm our results. So let's go ahead and create our vector called vec. We'll use the vector macro 1, 3, 5, 7, and 9. And now we're going to store our results in a result variable, which is going to be a vector of type I16. And now we are going to create an iterator over our method. We are going to map the values and use a closure and multiply all the values by 10. And then we're going to collect the values so that we can store them in our result variable. So map is going to allow us to execute a closure over each element yielded by the iterator. So in other words, the closure is executed for each element in the vector of numbers. So our iterator is going to provide us with this x value, and now we are going to modify that x value by multiplying it by 10 and store the result in our variable. So now we want to print out all of our variables to make sure that we got the appropriate results. And we see we have 1, 3, 5, 7, 9, and now we have 10, 30, 50, 70, and 90. So our solution for this is correct. I hope you enjoyed this assignment so that we could reinforce the learning that we gathered through this section of iterators and closures.